don't know me, I'm Akil Zagli. I'm a postdoc here at UC, and I'm very happy to introduce our next speaker, Irene Shivaei. Irene got her PhD in 2017 at UC Riverside. She is now a NASA Hubble Fellow at Stewart Observatory at the University of Arizona, where she is a member of the JWST MIRI and NearCam science teams. And today she'll be talking to us about dust in the early universe.
Thank you. Thanks. Thanks everyone for having me here. It's a pleasure, and especially thanks to the organizers for putting together this very nice gathering. So I want to talk about what do we know about dust at high redshifts, and where will we go with our future facilities, particularly James Webb Space Telescope. Dust is everywhere in the ISM. It's an important component of the ISM. It plays important roles in the physics and chemistry of the interstellar medium. For example, it facilitates star formation, planet formation. It provides surface for formation of certain molecules. It influences the ISM dynamics, the magnetic fields in the ISM, and many other important roles. It's also very important in terms of from an observational point of view. It absorbs and scatters UV and optical photons and re-emit them in infrared, significantly modifying the view of galaxies. So it's very important to characterize dust, not only to understand the physics of ISM, but also to make sense out of our observations to derive the intrinsic properties of galaxies. So here I'm showing a spectral energy distribution of a typical late-type galaxy. This is luminosity as a function of wavelength. The UV light and UV and optical light is dominated by the emission from stars. In UV we have massive stars. As we go to the longer wavelengths, we get more light from the older population of the stars. And you see the emission lines from ionized gas and hot gas all around the spectrum. As you can see in the shaded region, dust in the ISM absorbs and scatters the UV and optical photons and re-emits it at longer infrared wavelengths. It can either be in mid-infrared. These are smaller dust particles that got transiently heated by absorbing single UV photons to very hot temperatures, emitting in mid-infrared, or the bulk of dust mass in the colder regime of the infrared emission. This is the dust particles that are in thermal equilibrium with their surrounding emitting at far infrared. Why should we care about dust, particularly at high redshifts? This is cosmic star formation rate density, the evolution of cosmic star formation rate density as a function of redshift. And as you can see, at redshift of about 2 and 3, we have the peak of star formation rate density. If we split this into two components of dust-obscured star formation and unobscured star formation, you see that at least up to redshift of 3 that we have significant, meaningful measurements, obscured star formation rate plays a dominant role. And if we only rely on unobscured star formation rate, we are basically missing most of the star formation rate in galaxies. In fact, studies have shown that down to a few solar masses per year in total star formation rate, the fraction of obscured star formation rate is more than 50%. So obscured star formation rate is dominating the star formation rate in typical galaxies at redshift of above 1. And at even higher redshifts, there has been a growing number of studies, some of which led by scientists in your department, that has seen signatures of dust at very high redshifts, redshifts of above 6. So dust exists even at these very high redshifts, the first 100 million years of the age of the universe. But how much do we actually know about dust? One of the questions is that how much constraints do we have on the shape of the IR emission from dust at high redshifts? In this study 2 years ago, we compiled a large data set from the literature for all galaxies that have significant detection in the infrared, at far infrared, to constrain the far infrared emission of galaxies at redshift above 2. And for redshift 2 to 4, we see that we concluded that for these ULIRG galaxies at redshift above 2, a LIRG template, a local LIRG template fits them best. But if we go at even higher redshift above 4, 5 to 7, there are signs that the shape of the IR emission is changing. It's moving toward warmer temperatures. The peak of the emission is moving to shorter wavelengths, warmer temperatures, and it's also getting broader. And this can be a sign of change of dust composition. The composition of the dust at these high redshifts are changing from carbon-dominated dust to silicate grains. There are other studies that also show similar results, as we go to higher redshifts, the temperature of the dust is increasing. But there are also studies that are not in agreement with the previous ones, not seeing a significant trend a significant trend of the evolution of peak of the IR emission with redshift. So there is not much disagreement in the literature. And the same story is true for the shape of the attenuation curve of galaxies. Even in the local universe, the shape of the attenuation curve varies from galaxy to galaxy. Here I'm showing 4 most commonly used attenuation or extinction curves with Milky Way in black, SMC in yellow, Calzetti attenuation curve, which is calibrated based on a sample of local starburst galaxies, and one of the sightlines of LMC. As you can see, there is a wide range of variation. The slope of the attenuation curves are different. Some of them show this broad, prominent feature centered at 2175 angstrom called the UV bump, the UV extinction bump, which is completely absent in, for example, the Calzetti curve or an SMC curve. And these variations are attributed to different things. One of them is the geometry. Different dust and star geometry can cause different variations in the attenuation curve, but they can also be due to different dust grain physics intrinsic to these galaxies. So for example, in lower metallicity galaxies, we have different dust composition and size distribution that can cause a different shape of the attenuation curve. There has been many efforts in the literature to constrain the shape of the attenuation curve. Here, particularly, I'm showing a few examples that look at this UV extinction bump. This is particularly important for high redshift studies because at high redshifts, we are mostly looking at the rest frame UV light of the galaxies, and understanding how to correct this observed UV light for dust attenuation impacts the intrinsic properties that we are recovering from the observed light. So the bump has been seen to various degrees in different studies. Some studies did not see any sign of the bump in their samples. So again, there isn't much agreement in the literature. Another way of looking at the variations of the attenuation curve is by looking at this famous IRX beta plane, which is basically looking at the ratio of obscured luminosity, IR luminosity, to unobscured luminosity as a function of UV slope, the UV slope of the continuum emission. And if you translate the attenuation curves to this plate, to this parameter space, they occupy completely different places. And again, in the literature, there have been efforts to look at where do high redshift galaxies place in this parameter space of IRX versus beta, and there hasn't been much agreement. The most commonly used attenuation curve is the Calzetti curve, but there has been recent indications that high redshift galaxies may lie on a steeper attenuation curve like SMC. So with all these questions and not much agreement in the literature, I want to outline these 2 broad questions that we need to address in the following years with our current facilities and future facilities. What type of dust do we have at high redshifts? What is the size distribution and composition of the dust at high redshift? Is it similar to what we have in the local universe, or does it evolve? And what are the dominant production and destruction mechanisms of these of the dust particles that we have at high redshift? Because we know the ISM conditions at high redshifts are different. For example, at from local universe. For example, at a given stellar mass, we have lower metallicities, harder ionizing radiations. So all these and the different age distribution of galaxies at very high redshifts, these will all impact the production destruction mechanisms of dust grains at high redshifts. And ultimately, addressing these two questions will constrain the shape of the attenuation curve and emission template of high redshift galaxies. And a sweet spot for addressing these questions is redshift of 1 to 3. This is the peak epoch of cosmic star formation activity. Galaxies were most active during this era. They were in the process of assembling most of their stellar mass. So it's an important era to study galaxy formation and generally dust properties in galaxies. But also, this is the highest redshift that with our current data sets and current facilities, we can get large, statistically large samples of galaxies tracing different signatures of dust, both in emission and in absorption. So for example, with our mid-infrared facilities, Spitzer, we can trace the mid-infrared emission from small dust particles. With our facilities that look at far infrared emission, wrist frame far infrared for redshift 2 galaxies, we can trace the emission from cold dust and larger dust particles. And with our ground-based telescopes and with Hubble, we can look at wrist frame, UV, and optical, looking at the absorption features from dust. And in future, with James Webb, we will build up on these studies, both in the wrist frame, UV, optical, and also looking at using MIRI instrument on James Webb to look at the mid-infrared emission of dust. So first, I want to talk a little bit about what we know about the mid-infrared emission, dust mid-infrared emission at redshift of 2. Mid-infrared aromatic bands, they are commonly attributed to PAH molecules. PAH molecules are these layers of carbon-based molecules with edges of hydrogen. They absorb single UV photons, get very hot, get to high temperatures, and emit at certain wavelengths in the mid-infrared. They are very abundant in space. You can see them everywhere in very different conditions in galaxies. They can account for up to 20% of the total IR emission of galaxies. And they are important for chemistry of the ISM, for example, formation of H2 molecules. So these molecules, they absorb UV photons, as I said, and they emit at certain mid-infrared wavelengths. The strongest one here I'm showing is the 7.7 micron band, which at redshift of 2 exactly is placed inside the MIPS 24 micron detector. So from redshift 1.5, about 1.5 to 2.5, using MIPS 24 micron, we are able to directly trace the emission from PAH molecules. And having the relatively high sensitivity of Spitzer, we can look at the mid-infrared emission of typical redshift 2 galaxies and converting that to total IR luminosity to estimate the obscured IR star formation rate and IR luminosity at redshift of 2. However, this conversion is not trivial. It's very tricky, and most of the studies in the literature that looked at galaxies, the mid-infrared emission of galaxies above redshift of 1, they are limited to very dusty star-forming galaxies. So here I'm showing 2 example studies. There are many more, but if you look at the colors that corresponds to redshift above 1, they are mostly limited to ULIRGs at these redshifts, very dusty star-forming galaxies. And at the same time, from studies at redshift of 0, many studies, we know that the intensity of PAH emission, which by that I mean the ratio of a 7.7 micron emission to total IR luminosity, so that conversion, it scales with metallicity. As we go to lower metallicity, PAH intensity decreases. It can be either due to the fact that PAH molecules do not exist at these low luminosities because we are looking at younger systems, both young in terms of the age of the start, but also chemically young systems, so they haven't been produced yet. Or it can be because at these low metallicities, the ionizing radiation is harder, so it's preferentially destroying these PAH molecules. In either case, this anti-correlation has been seen at a redshift of 0, and we looked at it at a redshift of 2 for the first time because it needs a statistically large sample with metallicity measurements. And we are getting these metallicity measurements from rest frame optical spectra for redshift 2 galaxies. So for instance, here I'm showing the ratio, the metallicity oxygen abundance from the ratio of N2 to H alpha optical lines. And the PAH intensity is constrained using the Spitzer 24 micron data for redshift 2 galaxy. And we do see the same trend, the anti-correlation that has been observed at redshift 0. pH intensity drops at around oxygen abundance of 8.5. It drops significantly to very low values. The interesting thing here is that this drop at redshift of 2 happens at higher oxygen abundances compared to what has been seen at redshift of 0. So this is by itself is telling us different ISM conditions at redshift of 2. There are independent studies using rest frame UV spectra of galaxies that shown redshift 2 galaxies are alpha enhanced, meaning that their oxygen abundances are at a given oxygen abundance, their iron abundances, their stellar metallicities are lower, so they have harder ionizing radiations. And if that's the case, we do expect to see destruction of PAH molecules at higher oxygen abundances compared to redshift of 0. But to really, in order to really tackle this issue down, we need to get to lower metallicities, lower masses. So in the background, in the small data points here are showing upper limits from Spitzer MIPS 24 micron. And as you can see, when we go to lower metallicities and also lower masses, most of our data points are undetected. So in that study, we used stacking techniques to get to these low mass and low metallicities, but the individual observations are mostly undetected in 24 micron in their PAH emission. And for example, below masses of 10 to 10 solar masses, the detection fractions are less than 10%. And these are, when I say low masses, these are not really low mass in terms of dwarf galaxies at these redshifts. They have 10 to 10 solar masses, so they are more or less in like typical galaxies at these redshifts. So to better understand the physics of these PAH emissions, we need to go to these lower metallicities, lower masses, and this is where JWST will be revolutionary. Here I'm showing a typical SED of an SED of a typical redshift 2 galaxy. And the color points are showing 3 sigma upper limits for 1 hour integration times with the Spitzer MIPS 24 micron, and this is with MIRI imager on James Webb. So MIRI, as you can see, has much higher sensitivity compared to Spitzer, but more importantly, it also has a smaller beam size, up to 50 times better spatial resolution. And if you have worked with the Spitzer data for high redshift galaxies, it's really hard to deconvolve the large beam size of a Spitzer for individual galaxies at high redshift. So James Webb will have higher sensitivity, better spatial resolution, making us able to go and probe the PAH emission in these low metallicity, low mass galaxies. But to me, more interesting than that, but just looking at the single pH emission and looking at the total IR emission and obscure the star formation rate, more interesting than that is that we have multiple bands with MIRI. With the Spitzer, we had only one single 24 micron band, and we were able to predict the obscure the star formation rate. But with 8 bands of MIRI, we can basically get a very low resolution spectra, R of 5, of mid-infrared spectra of galaxies at redshift of 2. And this will be the first time that we can actually study these mid-infrared emission for high redshift galaxies. And by look, so here in gray, you see the mid-infrared emission of a typical galaxy, redshift 1, 1.5, 2, and 2.5. They, the 8 bands of MIRI track different pH emissions. And by looking at the ratios of these different bands, mid-infrared bands, we can learn a lot about the properties of pH molecules in galaxies. We can learn about their charge size distribution, their molecular structure. So for example, here I'm showing a plot from Drain and Lee 2001 study that shows the ratio of 3 different pH bands that are highlighted here in blue for redshift 1 galaxy. And looking at these ratios, we can easily separate ionized pHs from neutral pHs. So we can learn a lot about the properties of these dust grains molecules at redshift of 2. We can also, using these very low resolution spectra, we can also constrain some properties of the emitting sources, as well as the, for example, ionization parameter of the interstellar medium. So these kind of studies that look at all bands of MIRI for redshift 2 will be revolutionary for understanding small dust grains at redshift of 2. But pHs not only produce these emission bands, they are also thought to be the origin of this UV extinction bump, the mysterious extinction feature that we see them in some galaxies, but not everywhere. And there has been radiative transfer calculations that showed that if we have certain sizes of these pH molecules with certain amount of them, we can produce these bump extinction feature to different degrees. So now to better study and explore the presence of this feature at high redshift, we need to use our ground-based facilities, Hubble, and in future NIRCam and NIRSpec on James Webb, to look at the rest frame UV and the spectra of redshift 2 and 3 galaxies. But it's not only the bump, it's also the slope of the attenuation curve that is very important. As I mentioned, as we go to higher redshifts, UV light redshifts to longer wavelengths that are better accessible for us with our facilities. So it's very important to understand what is how the slope varies from galaxy to galaxy to correct our observed UV and optical light. So here, as an example of to show the importance of the constraining the slope of the attenuation curve, I'm showing a histogram of the ratio of H alpha to UV star formation rate. H alpha is robustly dust corrected using other Balmer lines, H alpha and H beta. But UV here is corrected once with SMC attenuation curve, which is steeper, and in purple, the Causetti attenuation curve is used. And as you can see, not only we have a large systematic uncertainty between the assumption of these two attenuation curve, but also we think that this large scatter that we see in this ratio is part of it mainly is caused by uncertainties in dust attenuation correction from dust attenuation curve from galaxy to galaxy, because we are assuming a single attenuation curve for all of our galaxies, which is very simplistic and probably not true. And by that assumptions, we are just adding more uncertainty to our measurements. So now, how can we constrain the shape of the attenuation curve in rest frame UV and optical? One way to look at it is to use rest frame optical spectra, the H alpha and H beta nebular lines. and compare them with their theoretical value. So the ratio of H alpha over H beta for certain conditions of the ISM, the electron temperature, electron density, is known to be this value of 2.86. And because of their wavelength separation, the ratio, if any deviation from this theoretical value will tell us how much dust reddening we have in our galaxies. So we define this quantity, Balmer optical depth, which is basically the ratio of observed H alpha to H beta compared to their theoretical value. And now if we sort our galaxies that we think have the same intrinsic SEDs, if we sort them from less to more heavily dust-obscured beams based on what we get from their Balmer decrement values, we can look how they change in these beams, and by comparing the dustiest beam to the least dusty beam, we can basically derive the shape of the attenuation curve as a function of wavelength. So in blue, I'm showing the average SED of galaxies that on average have 0 dust. And as we get to yellow and red, we have our galaxies on average are more dust obscured. And as you can see, the red one, that is the dustiest one, the UV and optical is completely suppressed because of presence of dust and higher dust reddening. So by looking at the ratio of these average SEDs, we can derive the selective attenuation curve, which is basically the shape of the attenuation curve as a function of wavelength. So for this study, I used the large spectroscopic sample of redshift 1 to 3 galaxies from MOSDEF survey. This was a survey done with MOSFIRE multi-object near-infrared spectrometer on Keck. It was a 4-year program, a large program on Keck, and at the end we have 1,500 rest frame optical spectra of these galaxies, covering all the main optical emission lines from O2, O3, the Balmer lines, N2 and S2. And this data set has been used to study different properties of redshift 2 galaxies, their metallicities, the ionization, excitation properties of the ISM, but also dust properties and star formation rate, specifically using H alpha and H beta ratio. So from this sample, I selected a subsample that I think they have intrinsically similar SED shapes. So I'm removing, for example, AGN galaxies, quiescent galaxies, those that have very young ages, where the variation in the UV slope is mostly caused because of the young age and not dust attenuation. ULERGs and very dusty IR bright galaxies are removed because they are optically thick to Balmer lines, and the ratio of Balmer lines are no longer indicative of the total dust attenuation in these galaxies. And most importantly, for all of our sample, we have metallicity measurements using other optical lines. So using that sample, the goal is to derive the selective attenuation curve. Here in black, I'm showing SMC, in green, Milky Way, and the local starburst attenuation curve is in orange. And here is our result. We see a steeper slope compared to the Calzetti attenuation curve and a weak sign of the UV extinction bump. Now, if we think about the more about the UV extinction bump, if we assume that this is caused by the PAH molecules and connecting it to the study that I showed you before, that pH intensity correlates with metallicity, we would expect that at low metallicities, where we don't see much emission from PAH molecules, we would expect to see to not see any sign of the UV extinction bump. And as we go to higher metallicities, we expect to see a very strong extinction bump because we are seeing an increasing pH intensity in those galaxies. So we divided our sample into these two metallicities. And here are the results. For the low metallicity attenuation curve, we see a very steep slope. and no signature of the UV extinction bump. But then if we look at the high metallicity beam, there is a very strong, significant UV extinction bump, which is indicating that these, the bump carriers are strongly present in these high metallicity galaxies and completely gone in the low metallicity galaxies, consistent with what we had before for the pH and metallicity variations. This is the first time that the variation of the attenuation curve is studied as a function of metallicity in a large statistical sense. And you may have, so this study has been done at redshift 2. It's much harder to do a similar study at lower redshifts, mainly because at lower redshifts we have very limited constraints on the UV part of the SED. As we go to higher redshifts, we have more data because the UV is moved to optical wave, is redshifted to optical wavelengths, and we have a better constraint then, so we can actually look at the variations of the rest frame UV. And in the last few slides, I want to talk a little bit about what we can learn with if we look at far infrared emission of galaxies, mainly using ALMA. So Herschel probed the peak of the IR emission, which was revolutionary in better understanding the obscure star formation rate contribution to total star formation rate. But using Herschel to study redshift 2 galaxies is extremely difficult because it lacked the high enough sensitivity and angular resolution to look at individual galaxies at these redshifts. On the other hand, ALMA is a facility that we can use to look at slightly longer wavelengths, colder dust emission. So here, to better understand where, with ALMA band 6 and band 7, which part of the dust we are actually probing, this is an SED of a local galaxy that is decomposed into two parts, the cold dust emission and the mid-infrared power law. And ALMA band 6 at redshift of 2 and higher will probe this cold dust emission on the tail of the Rayleigh Jeans emission of dust. And ALMA is sensitive enough to actually give us detections for typical redshift 2 galaxies. However, the problem is that ALMA beam size is very small. So here again, I'm showing this SED, far infrared SED of a typical redshift 2 galaxy. And the points are 3 sigma sensitivity limits for 1 hour integrations in different instruments, Spitzer, Herschel, and James Webb. So the difference between ALMA, as you can see, ALMA, Spitzer, and James Webb, they all three of them can detect these redshift 2 galaxies. But the difference is that with the Spitzer and MIRI and James Webb, at a single field of view, we can get many more galaxies, tens and hundreds of galaxies at the same time. But with ALMA, 1 hour integration gives us one source, or if we're very lucky, at most 2 sources that are fit in the small beam size of field of view of ALMA. So this makes it very challenging to construct large samples of galaxies that have ALMA observations. Because of that, all the current ALMA high redshift surveys are shallower than required for detection of typical redshift 2 galaxies. Most of them are limited to around 20, 30 galaxies that are all very dusty and star forming. In fact, the study that I showed you in the beginning of the talk, that we constrained the shape of the infrared emission for redshift galaxies at redshift 2 and 4. This is a compilation of all the ALMA observations so far, well, up to that date, that was published in the literature. But the average IR luminosity of this sample is 6 times 10 to 12 solar luminosities, and it's pretty high for redshift 2 galaxies. So these are dusty star-forming galaxies. And we actually have no idea how the Rayleigh Jeans tail emission of lower luminosity, lower mass, lower metallicity galaxies vary. Here, the black points and the gray points in the background are showing redshift 2 samples. And in these 3 colors, I'm showing templates of 3 low luminosity local galaxies. And as you can see, there can be 10 times difference in the ALMA observations of these low metallicity galaxies. And we have no constraints similar to these for higher redshifts. So what we need is deep ALMA observations that for a carefully selected sample of galaxies that span a wide range of mass and metallicity and have the key ancillary data that give us the important properties of galaxies such as metallicity. So in this last cycle of ALMA, we were awarded a 38-hour ALMA observation to look at the dust continuum emission of redshift 2 galaxies. And all of our galaxies have robust metallicity measurements. This is from rest frame optical spectra. They all have detect significant metallicity measurements from optical lines. And they lie on the star formation rate stellar mass relation. They are among the typical galaxies. And as an example here in the red box, I'm showing the galaxies that were used in one of the high redshift studies that were only limited to these massive, more star-forming galaxies. And we are pushing the limits to lower mass, lower star formation rates. So the observation hasn't been started yet, but I'm extremely excited to get the data and to finally put some constraints on the variations in the cold dust emission of redshift 2 galaxies and using that in dust theoretical models to put constraints on dust production and destruction mechanisms. So going back to the first 3 key questions that I outlined, we want to know the type of dust that exists at high redshift, the destruction and production mechanisms of dust at high redshifts, and finally constrain the attenuation and emission of dust as a function of redshift and galaxy properties. So I hope that I convinced you that the key to answer these key questions is to have multi-wavelength observations, and the first step will be doing that at redshift of about 2, not only because it's an important era in the history of the universe, but also because with our facilities we can get statistically large samples that probe different signatures of dust, both in emission and in absorption for galaxies at these redshifts. I showed that using mid-infrared emission, we can trace the emission from small grains and PAH molecules. These molecules may not be as abundant as at high redshift as we have in the local universe, because galaxies at high redshift at a given stellar mass, they have lower metallicities, they have harder ionizing radiation, and destroying these small dust grains at redshift of 2 compared to 0. And I showed that using far infrared, we can trace the emission from the bulk of the dust mass, and a different dust composition at high redshifts may result in large variations in the emission of cold dust, Rayleigh-Jeans tail emission of these galaxies. And we've attempted in many studies to understand the changes in the variations in the variations in the shape of the attenuation curve and infrared emission of galaxies. And it seems like the key quantity that we should look at is the metallicity. And it's hard to get metallicities for large samples of galaxies. It will become extremely easier to do these studies, not only down to lower masses, but also out to higher redshifts with James Webb. So I'm part of 2 large GTO programs, extragalactic programs with James Webb. The one with MIRI is focused on the Good South field in HUDF, which is on top of the footprints of the joint NIRCam and NIRSPEC GTO that are going very deep, not only in Good South, but also in other candles fields, deep extragalactic fields. And using these, James Webb have higher sensitivity, but it also, because of its wavelength coverage, we will be able to explore the dust attenuation curve to higher redshifts, higher than redshift of 2 for large samples of galaxies. And as I mentioned with MIRI, we will be, for the first time, we will be able to look at the variations of the mid-infrared bands at any redshift higher than 0. So with this, I will leave you with my summary slide. Thanks.
Any questions?
So that was an excellent review, Irene. I really enjoyed it. I have 2 questions. The first is more concrete. So when you're splitting up and the sample by metallicity to investigate the attenuation curve, and you see the bump in the low metal or in the high metallicity sample, is that split along the same metallicity lines that you see the pH deficit at low metallicity from your other study, or?
Yeah, that's a very good point. Yes, it's exactly a split at the same metallicity, and I think that's the key, one of the important things about this work, because if we only rely on studies that are done at different redshifts or even with different samples, there are many uncertainties in deriving this metallicity. So the oxygen abundance, if we derive it from different lines, we end up getting different oxygen abundances because there are uncertainties at redshift of 2 for these calibrations. These calibrations are all done at redshift 0. But I think the novelty of this study is that we are using it consistently for the same sample. So wherever we see this drop for the oxygen abundances that are derived in a certain way, we use the same division for this other study. So I think my point is that the oxygen abundance of 8.5, that is not the key. That is not the key point of this work. The key point is that at a certain oxygen abundance, however you want to calibrate it, we are seeing this change in the attenuation curve that exactly corresponds to the change in the pH intensity.
Cool.
Yeah.
So my other question had to do with, in this work you were limited because we don't have Spitzer IRS spectra for everything, of course, and so in dealing with broadband, photometry, how do you deal with and how will you deal with JWST and thinking about AGN torus emission and the possibility that there is also, in these higher mass galaxies, that there might be a possibility of brighter continuum emission that could, confuse this issue of pH versus
so with James Webb might be easier because we have multiple bands. And maybe we can decompose them and better understand the continuum if we go a little bit shorter, or the parts that are actually tracing the continuum, the underlying continuum. I'm trying to get to the, so maybe with James Webb will be easier, but to look at the contribution from possible AG. But for that study that we only had one single data point here, and we had no idea what is the contribution from the AGN, we tried to separate the AGN as much as we could using different AGN indications. So we used X-ray, we use IRAC colors, but also we use N2 to H alpha ratio because we had the optical spectra. So from these 3 ways, we tried to be very conservative in removing the AGN and hoping that's a clean sample at the end. Yeah.
From this figure, what kind of certainties do you expect to get from the blue points with the mirror photometry? Because the difference between Z of 1.5 and 2, they look very similar to me. What kind of uncertainties are associated with those points?
So the important thing is that for these galaxies, we will have very robust redshifts. So knowing exactly what is the redshift, then we can use a PAH model in the background to understand which these points are coming from which PAH feature. If you don't have the redshift, then yes, it's really hard to understand what's happening. But this study is for the MIRI GTO that is on the footprints of NIRCam with extensive rest frame, optical, and UV photometry that will constrain photometric redshifts to very low errors. So knowing the redshift, then basically, as it's shown here, you can reconstruct the PAH emission from different bands.
So this is also about your UV attenuation curve split on LC, and I was kind of surprised by just how strong the bump was in the LC sample, and I wondered if you had thoughts on why that was or what it means.
So it's very interesting because if I split the sample in any other way, for example in mass, because of mass metallicity relation, you would expect to see similar trend with mass. But in any other way that I split it, you don't see this. You do see a sign of bump in like more massive galaxies, but it's not as strong as this. The interesting implication for me is that there has been a lot of discussion in the community that maybe the reason that we don't see the bump in curves like SMC or Calzetti is not intrinsic to the extinction curve. It's not dust grain physics, but it's only radiative transfer effects. So it's the geometry or it's different optical depths of the galaxies that we are looking. So there has been a lot of studies that looked at how the bump strength changes with, for example, the axial ratio. So like whether you're looking at galaxies in edge-on or face-on. But I think the fact that we are seeing such a strong feature by just separating in metallicity, and I'm not putting any geometrical constraints on these galaxies. So it's a mix of all different types of galaxy, different orientations, just separated by metallicity. I think the important implication will be that even for the attenuation curves, the dominant factor that determines whether we have a bump and to what strength we have the bump is the dust. It's the grain physics. So it's the composition and also the size distribution, because depending on the size of the PAHs, you will get a stronger or weaker. But it's the dust physics, and it's not just the geometry that we are looking at. And knowing that, then the implication for high redshift would be using different attenuation curves for different samples of galaxies that you're getting. And having the mass or metallicity of a galaxy is much easier and more intuitive than like looking at the orientation of the galaxy. So.
One more quick question. Follow-up to this one. So when you showed in the, like one of the beginning slides, this cursor of Milky Way, LMC, and SMC, I could kind of see it in SMC, but I couldn't really see the LMC. And so, and there's lower metallicity than the Milky Way. So I was just wondering, have you tried splitting up this high metallicity bin in like different metallicities to see like how it scales with metallicity, and if the scaling is the same as at redshift 0?
Yeah. So. Yeah, you're right. In Milky Way, it's the strongest, and in LMC, we do see a bump, but it's weaker. And in SMC, it's either absent or it's very, very weak. Yeah. But for our sample, even so, this is the largest spectroscopic sample at redshift 2 that we have, near infrared spectroscopic sample that we have. And even with this sample, we only have about less than 100 galaxies in this high metallicity bin. And in order to construct the attenuation curve and construct these at least three bins of Balmer optical depth, statistically you cannot go lower than that, or your uncertainties would be huge. So 2 metallicity bins was the limit that I could push it to. But with NIRCam, this will be possible for much larger samples. And yeah, then you can actually look at increments of metallicity.
Let's thank Irene again.